And it's a great pleasure to be here. Um, I lived in New York for, up on the Upper West Side. I don't know which direction, but for 4 years. And so I really love coming back here and having the excuse to also meet a lot of great people is fun. So today I'm going to tell you about some of the things I've been thinking about with dark matter. It's been somewhat 40 years or something, 50 years that we've been trying to understand dark matter. So at some point I said, we need new probes. We need new, central densities, cusps, and halo shapes, and what all of these things are not proving to be useful. So let's look for what else we can look at. So I'm going to tell you about two things. I'm not sure they're any better than all the other things, but, I have to tell you what I've been doing. So, okay. So this is the outline of my talk. I'm going to tell you about this phenomena called figure rotation, which I'll explain. It's actually been known to be a property of CDM halos for 30 years, but it has been very little studied. And I'll give you some updated statistics on this in TNG 50 halos. And then I'll tell you about a new way to measure figure rotation in cosmological simulations using basis function expansions. I know there are several people who do dynamics here who are experts in basis function expansions. We've only just got started on it, so any feedback would be great. And then I'll briefly mention something that Adrian and I did a few years ago, trying to find a way to use tidal streams to detect figure rotation. And then I'll do a transition from being the scary theorist to pretending that I'm an observer, and tell you about the Dark Energy Spectroscopic Instruments Milky Way survey, and some new results on the GD1 tidal stream, which again, people here like Adrian and I think the workshop that discovered interesting things happened here. But we've been some new results, and I'll tell you a little bit about what to expect for tidal streams from DESi. Okay, so we know that that dark matter halos are assemble hierarchically, and that the accretion of dark matter, baryons, etc., occurs along filaments and is aspherical, right? It's asymmetrical acquisition of matter and therefore angular momentum, and this results in both tidal torques on the dark matter halos as well as internal rotation. So the typical quantity, which is called halo spin, actually encompasses two kinds of angular momentum. One is the angular momentum of particles which are sort of streaming around in the halo. And the other, if the halo is triaxial, is sort of a tumbling motion, like you would have if you sort of took a football and threw it, it would sort of tumble around in there. So dark matter halos actually have both types of motion. And so what I'm calling figure rotation is a term that's used in the context of stellar bars and is analogous to the tumbling of a football. So so that's what I'm going to tell you about. So we know from Lambda CDM simulations of like 30, 40 years that dark matter halos are not spherical, they're triaxial, they have like three unequal axes. They have very nice universal, and we don't really know whether the Milky Way disk is aligned perpendicular to the short axis or the long axis. That's a question we're still trying to understand, or at least a problem we're still trying to constrain. But we know that they have these dark matter halos in Lambda CDM have sort of universal density profiles with central density cusps. And there are hundreds of these dark matter satellites flying around In dwarf galaxies that we see in the local group, we don't actually measure these steep central density cusps. We see cores, and that's been a problem that we've called the cusp core problem. So these are sort of well-known properties of dark matter halos that most people are trying to.
That looks like a spherical profile, right? So you just told us that.
Yeah, this is just a spherically averaged profile. But even if you spherically average the density profile of these dark matter halos, they look like that. And if you try and find you do it in an ellipsoidal distribution, it is pretty close to being stratified on ellipsoids. So if you change that radius r to sort of an ellipsoidal radius, you get pretty much the same result. So it has been known since Dubinsky's work in 1992 and then followed up in the early 2000s that dark matter halos have this figure rotation. So you can see that this is an image from a paper by Jeremy Balin and Matt Steinmetz. And they plotted the major axis of the halo, and you can see it rotating with time. And this just shows that angle, and it's a fairly steady angle. And they found that 90% of halos had steady rotation of over a period of 1 gigayear, and then a somewhat smaller fraction, 50%, had steady rotation over 4 gigayears. And this was confirmed pretty much by Brian and Kress. But the numbers that they got for this pattern speed is ridiculously small, right? In 0.15 h, kilometers a second per kiloparsec. And for context, the Milky Way bar, which is also rotating, is rotating at between about 40 kilometers a second per kiloparsec. So it's just spinning around, and this is going around at 20-30 degrees per gigayear. So basically, people said this is too small to be interesting or detectable, and nobody looked at it. And we might conclude that that's still the case, but I think there's some useful ways we might look at it. So why should we bother with detecting this figure rotation? It turns out that it is common in Lambda CDM. So this is one of a TNG50 halo with a lot of the subhalos removed so that you can see it. And it occurs on a large scale. You can see coherent rotation out to 60% of the virial radius. And is likely, and it turns out that it's actually, because it's so extensive, is less affected by baryonic processes. So one of the problems with a lot of the other predictions of Lambda CDM is that the numbers that you get for subhalos or the values that you get for the density profile all depend on your baryonic prescriptions, and it's hard to tell what is caused by baryons, what's caused by Lambda CDM. So, but more importantly, none of these other measures of properties of dark matter actually test the dynamical nature of it, right? So if dark matter is a particle and congregates in these halos, and those halos actually move, then they are causing a time-dependent gravitational torque on things inside them. And so that tells you that it's not just some variation in something like MOND, which is sort of, there might be variations in time-dependent variations, but those can all be attributed to baryonic processes. Okay, so that's why we think that it's important. It requires it's sort of a dynamical probe of dark matter. So how do you measure figure rotation? The classic way of doing this was to define something. Take your particle distribution, define something called a shape tensor, which is sometimes called a moment of inertia tensor, find the eigenvalues of that tensor, well, diagonalize it, find the eigenvalues and eigenvectors, and that gives you the principal axis of this ellipsoid, and then by monitoring how the say the long axis or the short the intermediate axis changes over time, you can measure figure rotation. So this is called the sort of the plane method. You fit a plane through the major axis, and you get the rotation axis is perpendicular to it. So this is what was done before, but it assumes that your rotation is about one of the principal axes, right? And that is not necessarily guaranteed. And so we developed a different way to measure this, which, I mean, we meaning my graduate student, Neil Ash, realized, well, he developed this way, and I'll tell you about it in the next slide, but we applied this to TNG50 halos. One of the problems with this plane fitting method is because it measures the moment of inertia or shape tensor, it's very sensitive to a small subhalo at a large distance, sort of doing an orbit, right? So you need to remove any massive subhalos to be able to get the shape of the thing. So he removed all halos with at least 10% merger throughout the time scale, which was like about 4 gigayears that he was looking at in these TNG simulations, to remove false positives, picked halos in the range 10 to the 13 solar masses, and assumed that there wasn't more than 10% mass accretion between any two snapshots. So this is fairly restrictive, but it still ended up with over almost 2,000 dark matter only halos. And then in the parallel suite of dark matter plus baryonic simulations, we also got about 1,500 halos, right? So this just shows that all of these cuts actually did remove a bunch of halos, but between the baryonics, the simulations with baryons and without baryons, we had roughly comparable number of halos. So the other thing we wanted to do was to try and find a method to measure this figure rotation about an arbitrary axis. And it turns out that if you think about it, if you have something with 3 principal axes, which is rotating about a third axis, each of those principal axes will describe a circle. So this is some minor axis, or this the major, whatever. These different axes will describe a circle. And it turns out that those circles are all, each of those circles is perpendicular to the rotation axis. So even if you have, in an inertial frame, there is a unique axis which is perpendicular to all of these 3 planes. Okay, so, and that turns out to be very helpful because these halos are rotating really slowly. So you don't get a big track of its rotation, but you have 3 different halos, 3 different axes. They're describing 3 different planes. You can uniquely find that axis, which is perpendicular to all of them, to within 5 degrees accuracy, which is actually better than what you could do with the shape, with the previous plane fitting method. And so we went through and looked at all of these 2,000 halos with dark matter only and dark matter plus baryon. And this plot shows, it's this octant. So if this is the major axis, you're looking down 1 octant of your triaxial, of a triaxial system. The center is somewhere behind there. This is the major axis coming out here. This is the minor axis up there, and this is the intermediate axis of the halo. And the color shows the density of, or rather the probability that the rotation axis is aligned with the minor axis or the major axis. Just shows the probabilities, which you can also see in this plot. So here the orange points are for the dark matter plus baryonic simulations. The blue points are dark matter only. And you see that most of the halos are rotating within about 20 degrees of the minor axis. Another fraction are rotating within 20 degrees of the major axis. About 1% actually rotate about the intermediate axis. And they don't seem to be particularly unstable. They can rotate for 4 gigayears about the intermediate axis. And then there's a small fraction, about 30%, which rotate about just arbitrary axes.
Yes,
yeah.
So you said that this effect doesn't depend too much on baryons.
It doesn't.
So how do I see that from that?
I'll show you in the next plot. So basically these two distributions, I mean, if you do statistically look at those distributions, they're not very different from each other. And then if you measure the pattern speed, that is the rate at which they're moving. So the blue curve is the pattern speed for the dark matter only. The orange curve is for dark matter for baryons. They are, there is the dark matter for baryons, these are log normal distributions, is 14% faster. That, at least that median is. But if you look at the scale, this is, really small scale. It's undetectable. And the fact that 90% of dark matter only halos and 85% of halos with baryons show this, suggests to me that the two are really, comparable, right? I mean, it's not 100%, and we don't know that the Milky Way is doing this, but, the baryons would not have significantly affected it. At least that's the main idea, okay? So, and the median is about 0.3 kilometers a second per kiloparsec, which is, as I said, about this 15 degrees per gigayear. So there has been some previous work trying to see if you can detect figure rotation, and the idea was to use the fact that if you have a disk which may be misaligned with the halo, and the halo has a slightly different rotation axis, it could produce warps. And so this is work from Dubinsky and Chakrabarty from 2009, and they took cosmological simulations, they calculated the torques from both the large scale structure as well as from the figure rotation of the halos. And then they imposed those torques. They didn't actually put disks in a full cosmological simulation, but they imposed those torques on n-body disks and found that, you have fairly long-lived warps produced. But it's been, there's been very little work because it's actually, there are many different ways to produce warps. If gas falls into a disk at some random angle, it can produce warps. If you have a massive neighbor like the LMC, Milky Way has a warp, but there's good evidence that the LMC is doing some of it. And then recently there's been some observation, some expectation, or at least some observations or claims that the dark matter halo in the inner region is sort of tilted, and that might be causing warps. So there are many different things that cause warps. And anyway, this is an idea that exists. It hasn't been applied very much. And actually one of my students is looking at this also in the TNG 50 halos, but we don't have much to say about it right now. So another way that figure rotation we think can be detected was something that Adrian and I explored a few years ago, and that is the idea that this dark matter halo, as it rotates, can produce a time-dependent torque on tidal streams, right? Tidal streams extend out to very large radii. So this is just, it's not to scale, but this is an image of the Sagittarius tidal stream. It extends out to like 100 kiloparsec at one end, and at its closest, it's about 16 or 20 kiloparsecs from the galactic center. So it spans a large range of radii. So if the halo is rotating, you might expect that different parts of the stream will see different with different forces at different times. Okay, and so the net acceleration in this kind of potential is, of course, the standard grav. If you're looking in the frame of the halo, which you can do, it would have both the gravitational component, that's just the grad phi, plus a Coriolis acceleration, and a centrifugal acceleration. And so you can, for this, something like the Sagittarius stream, you can look at how these different accelerations vary as you go across the stream. So just to remind you what Coriolis force does, this is just something I got on, I don't know, Wikipedia or something. If you have a turning table and you send a ball across it, it's sort of in the frame that is rotating, it appears to sort of, it gets some, it looks like it's getting, moving, the trajectory is moving. And so if you look at the Sagittarius stream, and in this case, I think I just rotated it, assumed a Milky Way halo, slightly oblate, triaxial, assumed that it is rotating about the short axis, about an axis which is perpendicular to the disk. And this red curve just shows the ratio of the Coriolis acceleration to the gravitational acceleration as the orbit goes, so it's doing something like this. But as it goes around, and you can see the main point I want you to see that it is that the Coriolis acceleration can get as high as 15% of the gravitational acceleration. So it's not a small quantity. Okay, and that it happens actually doesn't happen way out. It happens about 30 kiloparsec, which is a region where we can actually detect things like proper motion, and we can make measurements which might be useful. And this is the same thing, except in this case it's rotating about the y-axis in the Milky Way coordinates, which is sort of parallel to the direction of the sun's motion. And so there you see it's not decreasing very much, it's sort of going back and forth, and that's because that axis is perpendicular to the stream. So it's like the stream is seeing this, it's being torqued in that way. Okay. So this is quite significant, and if you make a plot, you see on the Sagittarius kind of stream again and plot this acceleration, you see that it varies not just radially, but also at different, depending on the velocity of the stars, and both the sign and the magnitude change. Okay, so the paper that Adrian and I wrote, we looked at we weren't really trying to fit streams, fit the Sagittarius stream, but we looked at various different types of halos and tried to look at how figure rotation affected them, and sort of there are many different tests in it, but the bottom line I'd like to let you go away with is that we were able to show that if you had figure rotation of about twice that median value, so the median value is like 0.3 kilometers a second per kiloparsec. If you had figure rotation in the Milky Way, which is twice that, right? You already mess up the Sagittarius stream much more than there is much less coherence in the Sagittarius stream than you actually observe. So we don't know what the value is, but we know it's not, it's not at the tail end of it. It might be zero, but at least it's not, we know that you can sort of set an upper limit on how much figure rotation there could be in the halo. So you can, of course, there are also effects on thinner globular cluster streams, and there are many of these in the sky, and we're getting lots of different, observations of them. And so this is sort of just what's called this is just a simulated stream in what are called great circle coordinates. So this is just the coordinate phi1 is always along the stream, phi2 perpendicular to the stream, this showing the leading arm, this showing the trailing arm. And in a static halo, if you plot the ratio of the derivative of phi2 over phi1, and that's the dotted curve, and the proper motion along the stream, the ratio of the proper motion perpendicular to the stream over the proper motion along the stream, you see that they line up pretty well. Like the motion along a stream is pretty much, well, along the stream. It deviates here because you're running out of particles. But when you put in figure rotation, you begin to see that the proper motion deviates from the direction of the stream. And that is because, as you can imagine, if you have motion along this direction and your angular momentum of your halo is in that direction, you get a force which is the cross product, and that will push the perpendicular to the stream. So you can get this kind of motion depending on how fast your halo is rotating. Okay, but those of you who are familiar with this field will say, all very well, but what about the LMC? LMC, we know, is a huge big neighbor which is perturbing the Milky Way enormously. And you probably heard from Nico Garavito all about how the LMC is producing a wake. It's producing this collective response. It's causing the Milky Way disk to move towards the LMC and so forth. And one of the things that Nico's work showed was that there's this large asymmetrical variation in the density distribution of the Milky Way halo due to the LMC. And there's been other work. This is from a paper by Eugene Vasiliev, who showed that this kind of metric, that is looking at the ratio of proper motion perpendicular and along the stream, is also significantly affected. That is these deviations for the Sagittarius stream, and in his models, Eugene's models, he was able to account for these completely by sort of considering the effect of the LMC. And there's also been other work by Dennis Urkel, which shows that the LMC produces the same kind of perturbations to the orphan stream. So we started thinking, okay, well, this is not great, especially if you remember in my whole thing about the TNG 50 halos, where we found all of this figure rotation. We took out any sub halo which was more than 10%. We just threw out anything, and the LMC is at least 25. Well, it may be 25 to a sixth of the mass of the Milky Way, so it's not small, right? We can't ignore it. But again, we realized from this work that Nico did that there are these, if you do something called a basis function expansion, the asymmetric variations in the potential manifest in the odd terms of the basis function expansion. So just to remind you what these basis function expansions are, you can divide the density distribution. You can sort of stratify it on sort of shells, and you can divide the potential into this set of concentric shells, and then you look at the angular dependence of the density along each shell, and you can describe it in a monotone pole, a dipole term, quadrupole term, or a octupole term, and so forth. And so these are what we call the L terms, and in each for each L value there is m going from plus or minus 1, which has these other configurations. So it turns out that that something like and you can determine the coefficients of these L and M values, and that gives you actually a flexible, time-dependent way to describe the whole potential. Okay, so the reason this is useful is that you can actually use it to measure figure rotation. So we did this experiment where we set up an n-body triaxial halo using a package called a gamma written by Eugene Vasiliev, and we rotated it, a nice idealized n-body halo, rotated it, and computed the quadrupole coefficients as a function of time. So this shows time, right? This shows each of these panels. So these are the quadrupole coefficients. So this is L equal to 2, M equal to 0. These are M equal to plus or minus 1, and these are M equal to plus or minus 2. And in each panel, this is the radius. Okay. I don't know if it's easy to see, but you can sort of see that the amplitude of this coefficient sort of oscillates back and forth across time. And the reason it oscillates is that as the shape of the halo comes into and out of phase with that particular quadrupole moment, you see an increase or decrease in amplitude. Okay, and so this is so we thought, well, let's try and see if we can use this on the TNG halos, and we picked a halo in the TNG simulations which we knew had figure rotation over the time scale that, using the shape tensor method. Okay, and so this is what it looks like. And keep in mind that for the shape tensor method, we really couldn't go much beyond 4 gigayears look back time, but this shows all the way back to the start of the simulation. And I don't know if you can see this, but I think this is pretty similar to what we saw in the idealized halo. In fact, it's sort of even tighter, but there's some stuff here. So you don't see that here, but here you see this very definite oscillation in the amplitudes of the coefficients, going back to 8 gigayears, right? It doesn't start much before that, but you see these coefficient values oscillating in different components. They're out of phase, which you expect because of the, if you look at the shapes of those coefficients, you expect some of them to be have low amplitude when the others have high amplitude. So it's clear that this system, which we already knew had figure rotation, shows a clear signature of figure rotation with these basis functions. So we said, well, what's happening here, right? What is that?
Sorry, quick question.
Yeah.
I just want to be sure. The y-axis is the bottom earlier or later?
This is look back time. So this is now, and this is earlier.
Okay.
Right? So we wanted to know what was happening at a look back time of like 9 here, right? What's happening here? So you can look at that, and we looked at this also in the dipole coefficients. Those are also there, right? It's not just the quadrupole coefficients. And what you see here is a ringing here in the dipole coefficients. And when we went back to the simulations to look at what was happening there, we saw it was a 1:3 merger, which it oscillates back and forth. It produces, that's what the M equals 1 mode is. L equal to 1 is, it's a dipole mode. So as the satellite oscillates back and forth, it produces this, but then it disappears, right? I mean, it's there, it's very weak, but it's pretty much gone. And the time that it's gone is when this is happening. Right? So this merger came in, it basically transferred angular momentum to the halo and set the halo spinning. So, this is cool because not only do we know that halos rotate, but we know that mergers produce these rotations, right? And if we've had a major merger, like the Milky Way is supposed to have had a major merger with Gaia and Enceladus, I don't know, 8 years ago, maybe we could still see that. I mean, if it's not been completely perturbed by the LMC. So this is really interesting to us. And so, yeah, so this low amplitude here tells us that the merger is pretty much over. Okay, so there's this extended period of figure rotation. So, we'd like to be able to measure things like the pattern speed and the orientation of the axis. Yeah.
Sorry, so that was on one example of one merger. Do you have like a statistical sense if you could produce a similar signal if you had many minor mergers, or is it truly only of one major merger that you would produce it? Like if I measured figure rotation, would I be convinced that there was a major merger in the history of that galaxy?
I think so we've been doing a lot of different studies of, that same sample of halos, and we don't see much figure rotation when mass ratios is less than 1:10. Like less than 1:10, it does produce some effects, but I don't think it actually it seems to produce major mergers. So but that's a work in progress that we're trying to understand. Okay.
Thank you.
So do you want to measure the pattern speeds and so forth? So there's this method called there are these things called the Wigner-D matrices, which you might have encountered in quantum mechanics. I don't know. Sometime in your childhood when you were, studying like stuff. But anyway, they exist, and they are designed to transform coefficients of multipole expansion in 3D. Okay, and so you can write down, you can use them to determine the pattern speeds. And so Neil did. Neil is astonishing. Between Eugene and Neil, I should just retire. They take care of things. I just give them some crazy half-assed idea, and then they run away with it and make it golden. So anyway, they picked this. So Neil used MCMC to try and constrain the angle of the rotation axis, the pattern speed, and these vertical lines basically show the values we got from the shape tensor method. And I actually believe, you notice that this is like, this angle here is at -8 degrees. I actually believe the Wigner-D matrices are doing a better job. I believe this number and not the shape tensor, because that's more sensitive to, and it's only accurate to 5 degrees. So anyway, this is great because you can do this. And I just want to, as an aside, before I move on to other things, mention that quite coincidentally, we started looking at a barred galaxy in the TNG simulations. And this was actually because Bill Chen, who's another grad student, thought he wanted to play with Neil's method for using basis functions. And he looked at this galaxy and said, wow, he was looking in the inner region and found this. So the stars are doing this bouncing around in color, which is the same thing, except that because stellar bars are rotating really fast, this is happening much faster on a much faster time scale. And then this particular galaxy was part of something called the TNG sub-box, which has 10 mega-year snapshots, about 10 mega-years apart. And so this is what it looks like in that. Now you can, incontrovertible, this is bouncing around. This is going back and forth, nicely oscillating. So we discovered that in this paper that we wrote, we found that there's a dark matter bar in the inner 5 kiloparsec, which is oscillating with the stellar bar at the same rate. But we used this formalism of basis functions and the Wigner-D matrices to calculate not just the pattern speed, but also use something called a complex wavelet transform. So the Wigner-D matrices gave us the pattern speed as a function of time over 8 gigayears. I don't think this has ever been done before, over 8 gigayears. This matches published work for this galaxy. And one of the interesting things you see, they're purple lines here, it's hard to see them, but the pattern speed sort of jumps up and down, but it decreases and it increases and those are all mergers. So whenever there's a merger, it brings in some new angular momentum and the bar spins up. So both bars on small scales, 3, 4, 5 kiloparsec, and the halos on large scales are being spun up by mergers. Okay, so this is really interesting. And so, just for more fun things that bars do, you can measure the rotation axis. And it turns out that this bar is precessing throughout that 8 gigayear time scale. It's just going around like this. Those, the angle of precession or the direction changes whenever there's a merger. And it's also doing nutation, right? So if you remember your classical mechanics from 4th year of grad school, where you did tops and you hated them, but they did something called precession and nutation. Here's a bar doing that. I think it's just bizarre. Anyway, it's fun. So that's my aside. Yay for basis function expansions. All right. So going on to the near future, which are better because I have only 10 minutes. We're looking at this sample, or we're identifying a sample of TNG50 halos. We're using these basis function expansions to calculate potentials, and then generating mock tidal streams in them to get a sense of, what are all the observable properties of isolated halos and halos with LMCs, because I think that because one is affecting the dipole component, the other is affecting the quadrupole component, we think that you can actually separate this if you have enough tidal streams across the sky. Okay, so, and this is basically the topic of Neil's thesis. So I'm going to make a very sharp detour and pretend that I'm an observer. And tell you about the GD1 stream in the DESi, which was observed with DESi. So this was done with a large number of people in the DESi collaboration, and just appeared in print 2 days ago. So I'm really happy because this was literally my first observing paper. But yeah, so and DESi is sponsored by the Office of the Department of Energy, Office of Science, and has lots of collaborators and lots of participating institutions. So DESi, if you haven't heard of it, is this 5,000 fiber robotically actuated spectrograph on the Mayol 4-meter telescope with a 3-degree diameter field. And this is what the focal plane looks like. It's got these 5,000 fibers. If you look on video, look on YouTube for videos of these, you'll see them moving around like little, and they can reorient in less than a minute. And so the DESi is extremely fast. It has three different spectrographs, the G, R, and Z band, and it is its main goal is to get to measure dark energy, and they, most of the observations are for high redshift stuff, but we do actually have observations here of stars. It was commissioned in 2019, and the main survey was supposed to last till the end of last year, but most of the main survey program, it's been such an efficient spectrograph that most of the main survey is actually over, the data have been taken. There's an extension being planned, but that's still, it's unclear. And there's lots of data which is already public, but in the end, we expect to get about 7 million stellar spectra, and all the stellar spectra in the main program are for stars which have been observed with Gaia. And it goes out to 19.5 magnitude. There's some additional stars which are observed, which go down to, as close as 20.5 magnitudes. So the accuracy is about, varies between 0.5 kilometers a second and 3 kilometers a second. That's the radial velocity accuracy. And it can go as high as 10 kilometers a second in the very red and for low magnitudes. There are already several million spectra taken, and about 800,000 of them were publicly released last year. I think another 2 million spectra are being released in April. So at least 2 million stellar spectra. There are, of course, lots of others. And so there's more in the literature, and I won't go into describing this. But the GD1 stream has been particularly interesting. So I'm talking about now another probe of dark matter, because it was discovered here at CCA, I think in a DR2 like hackathon by Adrian and Anna, that there was this feature here which is called the spur, which probably happened due to a satellite passing through, and sorry, a dark subhalo passing through, and it's a really interesting stream that a lot of people have been looking at, and so we looked at it with DESi during survey validation. These magenta circles show all the 3-degree DESi fields which were observed, overlaid on a Gaia DR3 image, which has been with certain selections to make sure that we actually are able to pick out the stream. So it's not extensive in this data set, but there is some data. So there was in 2019, Khyati Malhan used something called Stream Finder, which is a method for sort of predicting line of sight velocities and finding stream members. And he argued that there was a structure here, which he called the cocoon, sort of broader structure, about 100 parsec in width relative to the thin stream, which is only like a 7 parsec or something, and a broader velocity dispersion. And similar structures have been found in a few other galaxies. So we, with the DESi data, we were able to, we first, did the same kind of thing, selecting in proper motion, and then selecting along a color magnitude diagram, which is appropriate for that stream, to identify the stars that seemed most associated with the stream. And then when you look at the radial velocities that you have in DESi, so the black points show DESi velocities, the other colors show radial velocity. So these are velocity in the GSR frame as a function of that along phi1 along the stream. And then when you look at only the stars within 30 kilometers a second from a spline fit to the stream track, you see this very clear peak there. And then if you look at the metallicity of those stars, you see that they're quite different from the background metallicity of the halo. And this metallicity sort of has a median value of about -2.4, which is consistent with previous observations of the stream. So we believe that we've actually identified the stream quite definitely. So we looked in some detail at this region, which was previously observed, called the cocoon. We sort of extended it, and you can see clearly that there are things which are offset. We looked at this region, which was where DESi had the most observations. We had identified about 100 new members and improved velocities for a few others. So if you plot the velocity difference between the stream and the stream track, between the star and the stream track against its displacement from the center of the stream, and then apply a sort of mixture model, you can separate a thin component from the broad component. And it turns out that the thin component is thin 0.15 degrees compared to the broader component. And the broad component is significantly hotter. It's like 7.8 kilometers a second. This is more typical of what you would expect for a globular cluster stream. Actually, it's a little high even for a globular cluster stream. But and about 60% of the stars belong to that thin component, and the rest to the broader component. And what's important is that these two have almost exactly the same, statistically speaking, the same metallicity. So they're not from background or something else. Do I have a minute? Yeah. 2 minutes? Okay. So, I didn't get into great detail, but one of the things that Khyati Malhan also looked at was ways in which you might produce this cocoon structure. And there are many ideas in the literature, and our paper is quite agnostic about what produces it. So you will see 4 different methods or 5 different ways to do it. But my favorite is the idea that this is if you have a stream, a globular cluster, which was accreted from a dwarf galaxy, which we think GD1 is based on its metallicity, it starts with some time in which it's evolving inside the dwarf galaxy, and then the dwarf galaxy falls into the Milky Way, and both of them are shredded, tidally shredded. But it turns out that if you have that kind of situation, you automatically produce broader streams. And one interesting thing is that if the halo, which brought in the dwarf galaxy, had a core, you get a slightly narrower stream than if it had a cusp. Okay, and so we find this to be true for all streams. They're quite extended, similar in length, say, to the GD1 stream. You can see a thin component and a broad component. We found many different metrics that you could use to distinguish between ways and between the mass of the progenitor and of the halo that brought it in. So I don't want to, we don't know what's producing this, and it might be, and I'm going to just say that we have a lot more data now, which is going to be released fairly soon. This is the year 3 data in blue. So this whole area has been observed by DESi. This is not the only stream we're looking at. In fact, we're looking to really hammer away at the GD1 stream. So this is the sort of the tiling pattern that we're planning with these 3-degree fields. So every part of it is going to have between 4 and 7 exposures to get as many stars as we can, down to Z magnitude of 20. We expect to get radial velocity uncertainties better than 10 kilometers a second. We're doing this also for many other streams. And so a lot of this data is going to be public soon. The Milky Way group is really tiny. So there's a lot of data already out there, which nobody's looking at. So please, and feel. In DESi, you meant? In DESi, yeah. DESi, there's just enormous amount of Milky Way data just sitting there, nobody's using, because we just don't have enough people. So I'm just going to leave the slide up and stop here. I apologize.
I'll let you direct questions, yes.
Oh.
There's time for some questions.
What's the limit on the radial velocity errors, and what we can improve to get better radial velocity errors?
Well, I mean, right now the limits is just based on exposure time. We have, the Milky Way survey sort of is sub what do you call it? It doesn't drive the survey program. It's really driven by cosmology, and so we get, and it's meant to be fast. So there's something called the effective exposure time of 3 minutes, which depends on what the transparency is and so forth. But this plot shows what we're getting right now. So we're getting 3 kilometers. This is 3 kilometers a second, 1 kilometer a second, half kilometer a second. So if you're going down to the faintest stars, you're down to 10 kilometers a second. But so for some of the streams that we are getting extra data on, we actually we're trying to get down to at least 10 kilometers a second. So we might expose deeper. So that's, yeah.
So I had a question. You had, when you were doing the tumbling halos, you had a plot of phi2 versus phi1 and the ratio of power motions as a function of phi1. And so my first question is, are those phi1 and phi2 with respect to the galactic center or with respect to some projected place of the sun in those simulations? Because phi1 and phi2 over long distances, if you're not.
Yeah.
So, but it's more complicated question than that, because I mean, did you have a triaxial halo in this? And was that triaxial halo aligned with this phi1 direction or not aligned with the phi1 direction? Because I'm surprised that, I mean, the thing is, you don't get it to be right along phi2 equals 0 unless you have specifically symmetric conditions. Do you understand what I'm trying to say?
Yeah, if you're, I mean, so so you do need to, so this, I think this particular example of a stream was a polar stream. Okay, so it is a special condition. It's not just a random thing. But a lot of these streams are not this long. I mean, this is a particularly long stream, but not all of them are this long. And you can still see these variations. And you do, you have to correct for solar reflex motion in order to get the.
So I guess my question was, so this is a special case where you can see a big deviation from the rotating halo. But how much is the deviation just from non-rotating halos compared to the deviation you get that you're looking for in a rotating halo?
Sorry, say that again. How?
So I think if you have like a triaxial halo and it's not somehow aligned with your stream, you would expect to see a deviation in phi2 and d phi2, d phi1.
Do you?
Near the edges. Yeah.
Near the edges, but yeah, I mean, in the majority of the stream, you don't see that much variation, even in a triaxial. Well, I mean, I think if it's very triaxial, yes. But this, I'm fairly sure I was just using some shape which is similar to, it's some slightly oblate triaxial with an axis ratio of 0.8 or something.
It's also galactocentric phi, not solar centric phi.
No.
Maybe.
Yeah.
Maybe
Follow up on
Yeah.
this.
Yeah, okay.
Great talk. I had a question about precession. Are there observational, can there be observational signatures in the tidal stream from precession?
Precession of the halo?
Yeah.
Yeah, well, this is just rotation of the halo. I haven't even thought about precession. We are actually trying to see if we can find signatures of precession for things like the bar, because there are bars which are like the LMC bar is not aligned with the disk, and so we're just wondering, is it precessing? Is that why it's but we don't know how common it is and whether. So we haven't thought of. Yeah, good question. I should think about it.
Yeah, thank you for the nice talk. I really like your discussion on phasor rotation. At the beginning, I sort of understood one of the selling points to be that it wasn't strongly dependent on baryonic physics. Of the probes that you outlined, do you have a good understanding of how sensitive those probes are to the baryonic physics? I guess I'm asking because if the thing we're trying to measure isn't sensitive to the baryonic physics, that's a great start. But then if the probe is sensitive to the baryonic physics, it maybe doesn't matter so much that the initial observable that we were targeting was baryonic physics independent. Does that make sense?
I don't, so most of the tidal streams that we focus on are things like globular clusters.
Yeah.
So I don't think the formation of globular clusters depends and their disruption, and most of that disruption is happening in the Milky Way, right? And it's being spread out in the Milky Way. So it depends on the overall potential of the Milky Way, but I don't think it depends on where the baryons are, because that tidal field is just coming from all the mass within, and its distribution, of course. So if you did a model without a disk, you wouldn't get the right model. But if you did a realistic model with baryons representing the Milky Way, I think it would be. I don't know if I'm answering your question.
No, I think you are.
Yeah.
You mentioned some relevant dependence on the internal structure of dwarf galaxies. Is they have cusp, of course. I didn't understand where that effect was coming from, because I think it's an important message.
Yeah, I'm sorry. I tried to put too much in. Yeah, so
and it was in your summary, stress. So.
Yeah, so so I did in my title. I said I was telling you two probes, and I only spent most of my time talking about one. So I felt at least my conclusions should have say something about the second one. But the idea was that there are these populations of accreted globular clusters, and they are thought to form in dwarf galaxies at high redshift, and then they get accreted by the Milky Way. Those dwarf galaxies with their clusters get accreted, and the dwarf galaxy disrupts, the globular cluster is released, it produces a tidal stream. And we think that they are accreted because they have lower metallicity than the globular clusters which are formed inside. And so it turns out that if you have a halo, if you have the in situ is basically a stream which is just formed in the Milky Way, is being disrupted in the Milky Way. The only potential it really feels is the potential of the Milky Way. But in this case, this dwarf galaxy is somewhere for a while. The globular cluster is in it, it's evolving. If the dwarf galaxy has a cusp, that globular cluster experiences a stronger tidal disruption than it does if it's a core, right? And the reason we think that this is an interesting probe is that people have been trying to measure the central density profiles of dwarf galaxies in the local group. And first, it's hard because they have very few stars. Some of them, like Fornax, do have globular clusters. Fornax has 4 globular clusters. It has a core. So it could well be that it always had a core, or it had enough star formation that it erased the core. But in any case, the tidal field from the Milky Way also affects the density profiles of dwarf galaxies. So if you have this early phase of tidal heating, which is happening long before the dwarf galaxy and the globular cluster fell into the Milky Way and experienced the tidal field, and that is still manifested in this structure of the stream, then it provides a different way to sort of probe these, the initial density profiles of these dwarf galaxies, which form these very low metallicity globular clusters. So yeah, so that's another area we're working on.
Let's thank Monica again. There's the usual reception. More time out in the hall.
Okay.